Welcome everybody, and thank you for logging into this webinar. Today's webinar is entitled Cables, the Weakest Link. My name is Justin Leonard from igus, and we work with moving cables and cable carriers. And the webinar today is designed to teach you a little bit about what you need to be looking for as a designer or machine builder when you look for flexible cables that will have a long life in your machine. The information we're giving here is good generic information which will help you. It's not designed to be a sales pitch. We're not particularly talking about just our products. We're trying to talk about good design principles that you should be looking for when you're specifying these products. So let's get started, and there is a question box that you have that you can click on and ask a question, and what we'll try and do is gather these up at the end of the talk, and I'll do my very best to answer them. So please do make use of that, and let's get started. So why are we asking this question about cables being the weakest link? Well, in modern machinery we're seeing the following trends. Of increasing speed and cycles in machinery, sometimes longer travel lengths, but equally machines needing to be more compact. And also another set of trends are that people need to have services between different machines talking to each other with very high accuracy, high data speed and high integrity. All of those things together really we could talk about being Industry 4.0, the idea of interconnected machines and factories. Now these trends together are leading to a lot of demands on cables which are moving. So anywhere where you have a moving part of a machine and a fixed part of a machine, then the cables in between those we are seeing more and more issues arising with these type of moving cables because of all of those trends. The typical things that we see are slow data rates, which is, for example, coming out of attenuation or interference. We're seeing weaker signals sometimes, and most commonly is intermittent signals and dropouts, which are the hardest ones to track down. And often our customers tell us they check all sorts of other parts of the machine, but in fact cables are often one of the first places you should look for when you get this kind of behavior. So what are the solutions? Well, one of the possible solutions that people were talking about in the past years has been wireless, and that it might be a cure for all of these ills. And on the face of it, that's a really good idea. We get rid of the moving cable completely. However, as our customers are using more and more wireless solutions within factories, we're seeing that there are accompanying issues of interference in a very crowded bandwidth, and also within, for example, metal structures within buildings, sometimes blocking signals or interfering with them. And then the other side of the same coin is, how do we feed power or indeed fluids, hydraulic or air, to something wirelessly? There are people working on the idea of inductive power, but that's still far from a reality. And as soon as your machine needs air or hydraulics, then of course that cannot be done wirelessly. What are the benefits of cables? Why are machine builders still using cables? Well, they're very cost effective, and you get a robustness of a physical connection, which again, talking about Industry 4.0, the idea of interconnectedness between machine, that robustness and physical connection is becoming more and more important. Also with cables, particularly for data or bus systems, fiber optic cables using light can solve many of the data issues. So you can still have a wired connection, but you can get rid of some of the interference issues that cables might traditionally have. So cables are still being used for those reasons. And so if you look at a cabled approach between moving parts of machinery and fixed parts of machinery, then that offers as a whole package a lot of benefits. You might put these together inside an energy chain or cable carrier, and that means you can then mix services up. You can have a number of services side by side: hydraulic, air, fiber optic, bus, power. And the whole packaged approach to this cabled approach means that you can upgrade and repair very easily. And then having a cable carrier or energy chain often adds protection and to that system as well, which will help with the reliability. So in order to understand whether cables really are a weak link or not, we need to understand why people operating machinery do experience failures and some of the issues that we talked about earlier. And so now I want to talk on this slide about the basic cable failure modes that we see. And these can be quite common. You may well have seen these yourselves. So the first one is core breakage. So this is an individual core, and where you have a strand, which I'm just showing here at the top of the slide, which breaks and then will poke through and then maybe poke into the next core, and then you get shorting, and that's where you get sort of shorting and intermittent effects. The next effect, which is quite commonly seen, is what we call corkscrewing, where the cable as a whole takes up this corkscrew type shape. And if you've ever handled this, you'll also know that the cable feels quite stiff, and that's to do with how the copper has work hardened inside. Other faults we see are things like screen rupture. So if you have screened cable for data or bus, if the screen breaks down like this, again, you have a lot of strands that can poke through, and you get two issues. One is obviously poking through and shorting within other cores, but also that if the screen breaks down, then electromagnetic interference can become an effect. And then the remaining issues are to do with the outside of the jacket. So sometimes the jacket will just split and rupture, like this diagram here, or you just get very, very high levels of jacket abrasion, either on the outer jacket or the inside cores, which will expose cores. This can be anything from really very dangerous to just allowing shorting and intermittent signals. Either way, it's not good. So what we want to talk about today is, can we square the circle? Can we get all the benefits of cables and a cabled approach from moving machinery, which will also work in this increasingly fast, compact, sometimes long travel, and in many cases tough environments that are presented by modern day machines? Well, of course, we believe the answer is yes. Now I want to talk about the type of good design of cable that you should look for when you're preparing to specify a cable for a machine that's moving, and I'm going to talk about what the design features are and why you should look for them. So here, for example, we have two cross sections. They will be similar, but one of them has thicker strands and one of them has thinner strands. And copper stranding for the core level is the first place to start looking for features and benefits. Now the right hand side has got quite thick strands, and you can see that it could behave like a paper clip. You bend those a few times and they could snap. So it would be intuitive to say the left hand side would be better because they're finer. However, it doesn't always follow. So if you go, for example, class 6 being finer, it doesn't always follow that they will work better than class 5. One of the crucial things is that the strands are optimized for the flexing life and for the application. However, some fine stranding is what you would expect typically for a good flexible cable. Next, we talk about the pitch length. Now, what I mean by pitch length, if you look at this little video here, which I'm just going to run and then pause, you can see the earth core through this cable is moving in a helix through the cable, and that's what we call a pitch. And the pitch length is the length from where it starts, one point in the cable, and then appears again at that same point in the cable. So here you can see from the frozen video here that's quite a long length before the core appears again. And what that leads to is a cable that essentially is quite straight extruded. The outer side gets stretched as it's bending, the inside gets compressed, and that effect starts to build up a lot of strain inside the cable. So this is what we're looking at, this very long pitch design. Also, in many cases, cables will simply be layered, again like this design here, where they're just laid up in layers. And what we've discovered is that there's a much better approach, which is particularly with high levels of multi-cores, that once we get to a 12 is to bundle. So very, very tight pitch. You can see the same position very, very quickly, but then bundling, taking these bundles and braiding them in the opposite direction. And what this means is that all the cores see a similar level of strain. Why is that important? Well, this is the real factor that drives the corkscrewing effect. And here you can see some corkscrewed cables inside cable carriers and energy chains, and this will show why that is. So as the cable is moving inside the energy chain backwards and forwards, and what's actually going on, as I just said, if we strip that down to just looking at a couple of individual strands, individual cores within this multi-core, you can see that one of these is being stretched and one of them is being compressed. And because they're away the neutral axis. That's quite a big relative movement, and what will start to happen is that there'll be work hardening of the copper, and you start to get this lumpy effect, which is what we call corkscrewing. The cable takes on a corkscrew type shape. If you bundle the cables and braid them with a very tight pitch, then, as I said before, all of the cores see a very similar strain, and you can see by the position of the earth core that it moves to the inside, to the outside, and back again very quickly, and all cores do the same, giving a very similar strain. And this is something that ensures that you have a cable which does not take on the corkscrewing shape. The next thing we want to look at is the design of the shielding, and on the left hand side we have a fairly typical standard cable shield which is wound from one direction fairly loose, but what we've discovered is that really doesn't work very well at all in a constantly flexed application. The reason being, as you bend it, the outside side here will stretch, and often these strands, individual strands, are being pulled quite a lot, and they'll break and they'll start to cause shorting or just opening up. On the right hand side we see a very tightly braided approach with a very shallow angle. If you look at the angle compared with the left picture, you can see this is very shallow, and that means that two things happen. As you flex this cable, the stretching effect on the strands is much less, and also that the opening effect and the allowing of electromagnetic interference is much less as well. So if we look at the next slide, you can see that as we take this cable and bend it, which is a standard so-called flexible cable, as we bend that, you can see you can just move the strand wires around very easily, which means they can open up and really don't offer the same level of protection. If we look at the right side, as we bend that quite slightly, you can see that there's really no opening up, and that shield remains intact, which is good from a perspective of electromagnetic interference. Next, we look at the jacket design. Now, what we're trying to do is we've on the right-hand side, you can see if we believe that this braided bundled design is a good approach. What we now need to do is lock that in place and ensure that it stays put. Now, most standard cheap flexible cables will have what's called a hose extruded or sleeve extruded outer jacket, which means it's very loose. That's put over the top, and it means the cores can move around underneath. The right hand side is something we discovered, that if you have a fully gusset filling pressure extruded jacket that fills in all the gaps and gussets around here, that locks that shape that you've built up with the cores in place and keeps it the way that it should be. And again, if we look at this with this video here, so there's a standard cable. The typical way that you can see that is you can just pull the outer sleeve and it comes right off. And on the right hand side, pressure extruder jacket, on the way that you can tell that it's really guarding the layup of the cable really well is that you won't be able to pull that off very easily. It means that cables are a tiny bit harder to strip, but actually that's a small price to pay for something which is going to last very well in the long run. Finally, when we're talking about outer jackets of cables, we want to look at jacket materials. Now, the two families of materials that most cable makers use is PVCs and PURs. And in some cases, you'll also see TPEs. We use this. This is a very high-grade material, thermoplastic elastomer family, which is very good for absolutely the hardest of environments. So PVCs are nice and cost-effective, but they are weak as soon as they come to abrasion, or if they're under UV light or temperature changes or oil, they can become brittle and fracture. PURs are much better for the above things, coolants and oil and temperature changes, and TPEs in fact are much better still. They're even harder and even better under different temperature ranges. But one of the crucial things to understand is that the term PVC, PUR and TPE is a very generic term. So PVCs and not all PVCs are the same. And we can show you, you can see this here, for example, from these photos. There are 3 compounds that we've been involved with developing, and you can see all of these are PVCs. They've all been subjected to the same abrasion test, but look at the difference here. So the bottom one, for example, the outer jacket has gone right through to the cores. The middle one has had some abrasion, it's almost flat, but nowhere near as much. And the top one has some marking, but really hasn't taken much off the outer jacket. Now, all 3 of those are still PVC and could be labelled as such. So it's very important when you're selecting cable to understand that the cable maker has an optimized compound, which is really well optimized for flexing, for abrasion and so on. If it's not, then you might find that it will be abraded very quickly, and you will lead to some of the effects that we saw earlier with the energy chains, where you can see worn outer jackets. Okay, so moving on now and looking at another very, very important aspect of cable design and development is testing. Now, the reason why we draw attention to this is that there's a standard test which is used to define a cable as flexible, and that's what you can see on the left-hand side. This is where cables are wrapped over rollers with a weight on them and moved back and forth over different diameter rollers, and then afterwards they're visually inspected for damage, appearance of breakage or whatever of the outer jacket. Now, this is a very, very simple test, and we don't think it gives a very accurate picture of how cables really behave in moving applications. And in a moment, I'm going to run a video that shows how we go about doing this. And this is something that's worth considering: is when you're specifying a cable, has it been tested in the type of applications that you're going to use it for? So if we look at this video, this is an example of our test lab, and it's just an example of how we believe cable testing should be done. And it's the sort of testing that should give you complete confidence in what's happening. So here, for example, you can see robots moving around constantly, different types of energy chain moving around the cable carriers. So here's a bank of ones which are being moved through twist. But all of the chains that are moving backwards and forwards contain cables that are being monitored continuously. The applications might be vertical or horizontal. They can be high speed or low speed, very small bend radius, very large bend radius. Long travel here, for example, there's one at 50 meters and another one at 120 meters, because that will behave differently. Robots, different styles of robots, and twisting type of applications. And in all cases, our cables are terminated into an automated test machine, which is picking up literally billions of electrical test results as we go. Also, we might be exposing at the same time the chains and the cables to different materials like coolant fluids or oils. Here's the automated electrical thing I was talking about. And in this way, we are truly representing everything that's going on. Here we have a climatic chamber that can go down to -40 degrees, which would typically make a lot of cable jackets brittle. Again, something that you could try and work out in theory, but will only ever really understand if you test in an application like that. Now I'd like to just look at a couple of very extreme examples where cables are used constantly, and the kind of things that can actually be achieved if the correct cable is specified properly. So here's an example of a very, very long travel in the Czech Republic. It's 615 meters long. It's the longest energy chain in the world. And this one is exposed to very high and low temperatures because of where it is, but also coal, dust and debris. And that's been running for many, many years now without any problems at all. Another application which I'd like to draw your attention to, it gives us another important feature of the cable design. So here, for example, moving cables might be used on a crane, but that crane might be in somewhere like Dubai and it might be in Russia. It gives a huge temperature difference. Let's say, for example, it's using a flexible fiber optic cable. Now that might become quite brittle at low temperatures. Particularly low temperatures might be vulnerable for it. And again, is this something we can work out in theory? Well, we don't really think so. We think the only way to do that is to test it in a proper environment that is representative. So here with this video I'm going to do is a climatic chamber that we believe this is the only real way to understand how the cable, or in this case the fiber optic, will fare in a constant flexing application in an energy chain. And this is moving backwards and forwards. This is just shy of -40 degrees, and there will be literally millions of cycles racked up on here. And again, this is all part of the goal of being able to say that the cable is absolutely guaranteed for 10 million movements or 3 years, or whatever your cable manufacturer can offer. And if this kind of level of testing is done, which it should be, then you can have complete confidence in that figure. Then we can look at things like torsion. Torsion is another very damaging component of flexible cable use, but with the correct design of cable can operate very successfully. And so here, an example of robots in pharmaceutical, even things like handling bricks or tiles, have very sharp, fine dust and debris around. And we again have many applications where with the correct design we've applied cables which can undertake millions of twisting movements. And again, that's something you need to consider, particularly if you're using robots. So that's concluding the this talk. I've just tried to go over some general areas there and answer this question. So our original question is, are cables a weak link for moving machinery? Now, I believe, and hopefully we've shown you more about today why we believe that with the correct design of a flexible cable, they do offer a robust and reliable means of power and data transfer, and that they can be used with complete confidence in moving machinery. So thank you very much for listening, and hopefully you've been putting in your questions during that talk. If there's anything that you wanted to know, there's going to be a few moments now just to give you some time to reflect on that, and if there's any questions you have for me, please do use the ask a question button and put that through. We'll have a few moments now while I collect those up and just go through them, and then in a couple of minutes time we'll start again and I'll answer as many of these questions as I can. Thank you. Okay, so we've had some questions coming in. Thank you very much for those. I'm just going to put these into an order and we'll go through them now and I'll answer them the best I can. So the first question that I've had in says, in your catalogue, some cables are labelled with a capital G, e.g. 4G 1.5, and some with an X, e.g. 4X 1.5, 4 times 1.5. What is the difference? This is a very common question that we get asked, and it's standard for some other cable manufacturers as well. What this simply means is that the X, the 4 times 1.5, simply means that there are 4 cores, each one is 1.5 millimeters squared, and when it's a times sign, it means that they are a coloured core, and when they're a G, it means that one of the 4 cores is a green and yellow is an earth. So 4G 1.5 would mean that there are 3 numbered cores and 1 green yellow earth core. If it was 4 times 1.5, all 4 would be identified by different colours. So I hope that answers that question. The second question I can see here is relating to the current carrying capacity of cables. And the question is, how do I see what current your cables can handle? That's a really good question because there's quite a number of factors involved in answering that. The first one is to understand what the inner insulation of the cable jacket is. That has a bearing. So we actually use 2 different materials, compounds, inner insulation. One is PVC and one is TPE. TPE is a slightly better insulator and therefore can carry more current for a given core size. So for example, 1 millimeter square, we can take 15 amps with our PVC insulation and 17 amps with our TPE. Now that on its own doesn't tell you all of the story. You also need to know what the ambient temperature is, and this again is a common thing across cables, but we have a way of describing it in some tables in our catalogue. As the ambient temperature rises, the current carrying capacity of the cable drops. It's not so efficient as carrying that current. And there's a modifying factor. So for example, once you get to 50 degrees, then you're at 71% of your possible current carrying capacity if you use PVC, and 82% with TPE, and so on. Finally, the other factor involved in that is what we call loaded cores, which just means how many other cores inside the cable are also carrying current, because that also has a heating effect, which will reduce the current carrying capacity. All 3 of these tables are to be found towards the back of our catalogue, but they're also good data to look for in any cable catalogue that you're looking in. They should all be similar, but you do need all of those factors to accurately understand, otherwise you can get caught out if there's a particularly high temperature scenario. So yeah, really good question there. And the third one, wow, this is a really interesting question here. Is there a way to accurately predict when a cable will break down a long way in advance, essentially so that it can be made a serviceable item? Wow, yeah, that's a really interesting ask. I guess this is going to be coming from somebody with a factory environment where production downtime is incredibly expensive, and so a cable failing or wearing out after a very long life, even after a very long life, it's important to understand when that needs to be replaced. That's quite a timely question. That's something we're looking at now. We have this under our banner of smart plastics. We're looking at the idea that a cable, as well as our other products, can be self-diagnosing. Now, if you think back to the slides a couple of slides ago where we looked at our test labs and the massive amount of data that we build up with millions of cycles under lots of different conditions, This is an area that we are now looking into very strongly, because we have all of this data. We can actually accurately predict, looking at the electrical properties of a cable in use, when it is starting to degrade in some way. And because we have the curves, the empirical patterns that will follow, we can say very accurately where it is in its life cycle. And the way that we do this is that under our smart plastics, we have something called CFQ, which is chain flex quality. And if we have 2 spare cores in a cable, we can connect these up to a sensor, an iSense, we call it iSense, but a sensor box, which is monitoring these particular electrical parameters that we understand well. And then we can start to see where it is in its life cycle, because we will have some lab data to back that up. So this is a really exciting new area that that our customers, particularly in areas, as I said, of expensive production, are very keen to get a grip on. And so with our CFQ, CF quality, this is something we now have a solution for. So if you need to know more about that, please do have a look at the website under Smart Plastics. So I think we'll leave that there with those questions. They're 3 really useful questions. If there are any more, I will get back to you personally and answer them for you. So thank you very much for all of you who've asked questions. If you do need any further information about our products, then you can see on the right-hand side of your screen there are my contact details. There is our website link there and my email address and so on. So please do get in touch, and I'll do my best to help you with whatever queries you have. So look out for further igus webinars in the coming months. We'll be doing more of these to try and share what we think is useful knowledge with you. Thank you very much for your time and attention today. Goodbye.